Good evening. Welcome to Krishna's classroom. What we do next is to give an alternative or equivalent definition of continuity. Before we go into this, we'll just recall the following. Our definition of continuity was in a metric space where we had the concept of a distance, and therefore we were in a position to talk about the convergence of a sequence, and we exploited this, and through convergence of the sequence we introduced the definition of continuity. But then when you go from metric spaces to topological spaces where you don't have a notion of distance, what you have is a collection of subsets called the open sets, and that constitute what is called the topology, which this collection shares the properties of open sets in a metric space, namely that it is the whole set is an open set, empty set is an open set, then arbitrary union of open sets is open, and finite intersection of open sets is open. Now these four properties we have proved in the case of open sets in metric spaces. And remember, open sets in metric spaces are defined through what are called open neighborhoods, etc. Starting from the notion of distance, we have this path distance to neighborhoods then you have open sets. That's what you have in a metric space. Whereas in a topological space, so this is about the metric space. Whereas in a topological space, we do not have the concept of a distance. We do not have, therefore, the concept of neighborhoods in the sense of balls or anything, but we begin from open sets. And in a metric space, we prove that X is open. So you take XD, a metric space, X is open, then the empty set is open, arbitrary union of open sets is open, and finite intersection of Now this is the basic properties of the open sets in a metric space. All these can be proved. Now we go one step further and go from what are called metric spaces to topological spaces. In topological spaces, what you have is X a non-empty set and a collection of subsets tau A subsets with the property that 1 with the properties 1 x and the empty set are elements of tau. Tau is a collection of open sets, of subsets. Then 2 tau is closed under arbitrary union by which union, that is, if A alpha is an element of tau for every alpha in an index set I, then union belongs to tau. That is what you mean by it is closed under arbitrary union. And third property is that tau is closed finite intersection. What does it mean? That intersection I equal to 1 to n AI belongs to tau So we have x, choose a collection of subsets of x satisfying these properties, which are the fundamental properties satisfied by what are called open sets. And we say call in the topological space So let us keep these things in mind, first of all. Now what we want to do is, primarily, we have introduced the notion of distance and introduced the notion of metric spaces to do analysis on general sets. So depending on the problem that is getting formulated mathematically, we choose the set X and we introduce a notion of distance on that set, and then you can do analysis on that. So the most interesting aspect is that when you are in a metric space, you have the notion of what is called convergent sequences, or the sequences which are convergent, sequences which are not convergent also. So convergence is something that you can introduce there. But of course, when you go from to the next level, namely topological spaces, this is not possible. But remember the way in which we have defined continuity. Now we'll come to that. So we keep this background, these aspects in your mind for what follows now. See, our role model for defining a vector space was the real line. So we have R, real line, and then we have the notion of a distance on the line defined as modulus of x minus, with the obvious meaning they are for every x comma y belonging to with the structure of R, all these are well defined, and this has all the properties of the distance. Now this is the distance notion that you have, and in all our statements regarding the convergence we make use of this. For instance, suppose you take a sequence R, and suppose xn, the sequence xn converges to x, say, by which you mean the following, that is, the distance of xn goes to 0, that is d of infinity. So everything is formulated in terms of this. Okay? For which, from you know what we mean by this distance goes to 0. This is equivalent saying that this is equivalent to given epsilon positive, there exists n depending on epsilon such that mod xn minus x is less than epsilon for every n Now this means the following. See that mod xn minus less than epsilon means xn belongs to the interval x minus epsilon to x plus, that is x minus epsilon less than xn less than epsilon. So you have surrounding the point x, you have x minus epsilon, x plus epsilon, and what we say is that xn turns out to be somewhere here or anywhere here in this interval for all n, for every n greater than or equal to n. This is the statement. So it has been recast or understood in the context of, or in terms of what is called a neighborhood of the point x. Now you see that this automatically gets pushed across in the context of a metric space. What happens in the case of a metric space? Suppose X is a non-empty set and D is a metric now. What you have is that you have D with D is a map from X cross X to R with certain properties, namely this is the symmetric property of this, that the distance from X to Y is the same as the distance from Y to X. And the third property is what is called the triangular inequality. dxy now with X as R and D defined in this way, modulus of X minus Y, all these three properties are satisfied. Therefore, these three properties of the distance is what is taken as the basic property to define a distance function. Okay, that's how the generalization goes. And now I'm spending some time on this to tell you how ideas gets pushed across in a more general scenario. Okay, now you can immediately recast this kind of thing. Suppose you take a sequence of points in X. Now we shall define Xn converges to X, the sequence Xn converges to X if the following is true, that is d Xn goes to 0 as n tends to infinity. Now this is equivalent to saying that given epsilon, there exists an n epsilon such that Xn belongs to Bx epsilon, where Bx epsilon is defined as the set of all y such that d of epsilon for every n greater than or equal to n epsilon. Just compare the two scenarios. So this has been generalized. Okay, and this is what you mean by convergence in a metric space. Now what we need is to talk about continuity. So we work on functions defined from, first we look at functions defined from R to R. So let f be a function from R to R. We say that f is continuous at x belonging to R if the following holds. Namely, what is it? If for every sequence xn converging to x, the sequence to the value of the function at the point x, that is R converges to x, f of xn, the sequence image points the value of the function at x. This is what you have. Once again, this is equivalent to the following. Let us examine this. The first part we can rewrite in this form. So xn converges to x means now fxn converges to fx means given epsilon where x is a n to epsilon. This is of course the set of natural numbers such that mod So these are the two statements and they are connected. I mean, they are going to be connected. We are going to connect it. Okay. So the connecting part is this. Okay. This is equivalent to saying that is mod xn minus x delta means that means we have now how are they connected? Let us examine this in detail, in continuity. Okay. Next, let us explore this and connect them up to get the notion of continuity. For sequences, it means that if xn converges to x, then fxn converges to fx. That's it. But what is it? Let us try to understand this. Let us look at the graph of a function. So this is essentially the set of points since we are taking R as a domain. I mean, otherwise you use the domain. So, okay. So, it is a set of points in R2. So let us draw the graph of that. Okay. Now, suppose this is the point X. Then you see that X gets mapped to a point Fx. This is Fx. Okay, let me just slightly. Now, what do you intuitively mean by continuity? What you want to say is that the neighboring points here gets mapped to neighboring points. So, what you have to say is that if you take a neighborhood of fx, then there exists a neighborhood of x which will get mapped into it by f. So, this is what you need. So, a neighborhood of fx is so a neighborhood of fx is And then so what we want is the following: the neighborhood of the points in the neighborhood of x should get mapped to points in the neighborhood of fx. So a proper expression of this is that suppose you choose a neighborhood of, so for a choice of an arbitrary of fx, there exists a neighborhood of x which gets okay, that's a qualitative one which is imprecise, and let us put this into, have a look at what is happening. So we have chosen a neighborhood of fx in this way. Look at this. So now, which are the points surrounding x which gets mapped into the chosen neighborhood? These are the points. Okay. Therefore, the question that you ask is this: does there exist a neighborhood? So this is x minus epsilon, x plus, sorry. Does there exist a neighborhood of x which will get mapped into the chosen neighborhood of fx? This is the question. So put it more precisely. Given epsilon positive, there exists a delta positive such that f of the interval f of this interval is contained in this is the definition, and this is the same as saying that if xn converges to x, then fxn converges to fx. That's the meaning of that. Okay. So given the epsilon neighborhood of fx, there exists a delta neighborhood which gets mapped into it. So what does it mean? It means that we are taking the delta neighborhood and which of these points go over to this. Now to understand this more clearly, you should look at a discontinuous function. Okay, let us choose a discontinuous. So let us look at this function. X. Okay. Fx equal to x for x and equal to x plus 2 . Now you see that clearly the function has f is discontinuous. Okay, let us test these notions. First of all, xn converges to x. Suppose you have a sequence xn converging to 1. Then you see that what about fxn? Fxn equal to fxn equal to xn whenever less than 1 equal to one. This is the definition. Therefore, you see that as n tends to infinity, if xn converges to 1, from the left, the sequence would converge to 1. So, you see that limit if xn is, and this is equal to 3 if xn greater than 1. That is the right limit, the left limit of the function gives the value 1, whereas the right limit will give you the value 3. And you see that the left limit and the right limit are different, therefore it is not continuous. But how does this fit into this language? You can see this. I mean, we are testing in the neighborhood of 1. So you take this value 3. 3 is the value of fx. So you take some neighborhood of this and then try to work out set of points which get mapped into it. You see that suppose you choose this neighborhood, say 3 plus 3 minus half is 5 by 2 to say, like, suppose this is the neighborhood to which 3 belongs to, which is equal to F. Now suppose you choose this neighborhood. Can you find, does there exist a neighborhood of 1 into this interval? What is the nature of the neighborhood? The nature of the neighborhood is that 1 minus delta. This is the nature of the neighborhood for some value of delta. Now you see that no matter how small choose epsilon by 2, where of course epsilon is here taken as 1 by 2. Okay. So you see that it is discontinuity. There does not exist any neighborhood of 1 which gets mapped into the neighborhood of this. Because if you take any neighborhood of this, these set of points go here. They fall out outside this interval. So they do not go there. So you see that any point here gets mapped into this. It's only these points which go into this neighborhood. So we can find a delta such that the interval 1 to 1 plus delta gets mapped into this interval. But if you take a neighborhood of 1 which consists of intervals of the form 1 minus delta to 1 plus delta, there is the portion from 1 minus delta to 1 does not get mapped into this portion. Okay. So what do we mean by continuity? So we can now formulate continuity here. Continuity is that f is continuous at x means given epsilon positive, that is for every epsilon there should be a corresponding delta. There exists a delta positive such that f of x minus delta to x plus delta, this interval is contained in try to analyze this in the context of this particular example. That will give you a lot of insight into this definition. Okay, so for any given epsilon, there should be a corresponding delta such that this condition is satisfied. Then you say f is continuous at the point x. Okay, now we go to the easy to generalize it. what will be the generalization in the context of? Okay. So in R, x minus delta, the interval this is a delta neighborhood of okay. What happens in X? D, a delta neighborhood is this. B X delta defined by the set of all y belonging to X such that the distance from is the delta neighborhood of is a so this is the analogous thing. So these two are to be connected. Therefore, now let us ask the following question. Suppose X let F be a map from X to Y and take X belonging to X, Fx belongs to Y. So X goes to X. Now we say that F is continuous so you have got so this is the epsilon neighborhood of Fx, whereas this is the delta neighborhood of X. Roughly this is the picture. I mean, I'm not saying that it's going to be always the shape of these balls are going to be like this or anything. Okay. And these are open sets, of course. The neighborhoods are open sets in the respective spaces. Therefore, what do we have? Delta which will depend on epsilon such that f of So this is the definition that gets formulated on this. Now you see that this is exactly f of in the interval x minus delta compare this. So for any epsilon positive, there is a corresponding delta such that this condition is satisfied. Then you say f is okay. In all this is what you have. You have a definition that has been done using the sequences, and probably on the real line everything is clear that if xn converges to x, fxn converges to fx, then f is continuous. That is equivalent to the corresponding statement of this kind. I mean, that is we have not given any proof of that yet, but that appears to be more or less clear for every sequence xn that converges to x, fxn converges to fx. Okay, so that appears to be very much equivalent to this one, but it's not obvious in the general context. Although you still have this concept of, say, d and this is this and this statement that f of it's not quite clear how these two are mean the same thing. So that is something that we have to explore. We have been working with this, and this was very comfortable, very handy in this case. And you can get away with it in a metric space. There is no problem, because these concepts are all well formulated. But now, when you go to topological spaces, this formulation does not work, because you don't have this notion at all. Therefore, you will have to reformulate it in some form like this, okay, right? And possibly the open neighborhoods would have to be replaced by what are called open sets in the topological spaces. And in a topological space, the continuity of, so suppose, okay, let me not go into it. I'll explain this probably in my next lecture, where I work with the mappings from one topological space into another. Okay, but this is the formulation that you choose. And then one more step from here, instead of taking the open neighborhoods, because you have the neighborhood notion in the metric spaces, whereas here in the topological spaces, that the neighborhood notion will have to be replaced by what are called open sets that contain x here, the open set that contains fx here. So given a open set V containing fx, okay, so you can easily work it out. We are now going to replace it by this. So suppose X and Y are two topological spaces. F is a map from X to Y. We are asking F continuous at X. What would be the equivalent formulation? You don't have neighborhoods anymore, but you are going to replace them by open sets because they are open sets. Okay, and then in terms of neighborhoods, you have the notion of open sets. So what you have is that given an open set V containing Fx in Y, that is V is an element of tau 2. There exists an open set U containing X. U is an open set tau 1, okay, such that that will be the definition. So our task is now to prove the equivalence of this. Now you have seen we have our role model, namely R, with the usual notion of distance, and we have the formulation of continuity over there, where you can do a little bit of graphs, etc., and understand the problem. Then we go to a more general scenario of working in metric spaces, where the distance notion gets generalized, and then you have the corresponding analogous definitions of continuity there. But then when you go from there to here, no more the sequential approach is going to work. So you will have to take the alternative formulation. If you can prove that these two are equivalent, you can take the alternative formulation and then recast it in the case of a topological space. So our objective will be to establish the equivalence of these statements in the context of a metric space. Thank you very much.